students, to the review sheet help video. Let's go ahead and get started with these problems and see if we can get you guys a little help. On page 525, the first ones, numbers 1 through 12, are these problems right here. Let's go ahead and see if we can help locate these, okay? The center of a circle, well, that would be P. Whoa, that's not good, is it? P or Q or R. Any of those would work. And so let's take a look at that. The answer would be P, Q, or R. Interior point of circle P. Well, the only point that I see inside of P is G. So the answer would be G or P also, of course. I wasn't counting the center, but I should have. That's my fault. So P or G. Number 3, chord of circle P. Well, the only chord that I see is AF. So we have chord AF. Diameter of R. Diameter of circle R. Well, this right here is not a diameter, but this is right here, LJ. How do I know that? It passes through the center of the circle. So LJ or JL. Number 5 is segment that is the radius of circle Q. So I'm looking for a radius here in circle Q. The only radius I see is QE. So QE, there we go. Alright, number 6, point of tangency on circle Q. Point of tangency on circle Q. Wow, now let's take a look at this for a second. We know that this would be a point of tangency, and so would this. But also circles can be tangent to each other when two circles intersect in one place. So we have 3 points of tangency. Any of those would work. C, O, or D, any of those would work. And there we go. A common external tangent now. An external tangent is a line, listen carefully please, that is tangent to two circles. Okay? However, it's tangent to two circles in such a way, if you were to draw a line between, okay, let's look at this line here. This line right here is tangent to two circles. Got it? Here and here. But if you were to draw a line connecting the two centers of those circles like this, does that tangent cross that center line? No, it does not. So we call that a common external tangent. Now, if this line right here had crossed that green line, then we call that a common internal tangent. But it's on the outside, we call it external. So BC is a common external tangent, okay? BC. Alright, let's take a look now at number 8. Now we're looking for a common internal tangent. Well, right here it is. Do you see this line right here, students? This line is tangent to two circles. That's the first thing you need to have a common internal or common external tangent. You must have a line that's tangent to two circles. Second of all, draw the imaginary line from the center of this circle to the center of this circle. Does this common tangent cross that line? Yes, it does. So we call that a common internal tangent. Common internal tangent. So it would be HI. HI. Alright. Now, what circle is congruent to circle Q? Well, I'm trying to see how we would know that. Let's see here. What circle is congruent to circle Q? I mean, it looks like this one here, but I'm trying to think how we know that for sure. I'm looking at the directions. It doesn't tell us anything about length or widths. We know that when two radii or two diameters are congruent, then the circle has to be congruent. And so I'm trying to check this out. It's obvious to me that circle R, I guess they want us to kind of eyeball it, guys, and just say this circle here, there's no way this circle here is congruent to the two smaller circles. So they're saying, if there's a congruent circle, which one would it be? Well, it would be this one here and this one here. Those two circles would be congruent. So circle R is congruent to circle Q. Now let me look one more time just for about 10 seconds to make sure I'm not missing anything. Okay, here's this. I don't see any lengths anywhere, any congruencies. Okay, moving on to number would not call this a secant line. Now, if the book does, when I unveil the answer, then that's one thing. But for me, it's a chord because it stops its endpoints like right in the circle. So that's not a line to me. That's a segment. I call that a chord. This is a secant. This is a line that passes completely through the circle in such a way that it intersects the circle in two places. So I'm going to say that line MK is the secant line they're talking about. So are there others? Let's see. LJ. Well, yeah, to me, LJ is a chord. AF's a chord to me, guys. I'm not going to split hairs over that. We'll go with what the book says, but that's just my opinion. Point of tangency for circle P and circle Q. Well, here's circle P. Here's circle Q. Where do they intersect in one place? Right here. So point O is the point of tangency. Number 12, exterior point of circle P. Well, students, look at all these. I mean, any point, I'm going to highlight them. Any point that is not inside the circle of P or on the circle is on the exterior. So all of these points here are on the exterior. All of these points here are on the exterior of circle P. So any of those would count. All of these points here either lie on the circle P or they're inside of P. But all these others are exterior points. Okay. Alright, let's continue on. Numbers 13 through 18. The directions say to find the lengths of the segment. Now, you should recognize this from your quiz. I don't do this very often, but this problem was on your quiz. We'll still go ahead and look at it again to make sure we understand everything. But this was on your quiz. And let's take a look at it again, okay? First of all, this is a radius here. It has a length of 4, okay? So we know this radius here has a length of 4. We know this radius here has a length of 4. And we know this radius here has a length of 4. Now the first thing they want us to find is IJ. Well, IJ has a length of 4. So the answer to number 13 would be 4. Now, IK. Well, if I'm going from I to K, think about it. From I to L is 4. And from L to K is 4. So the whole length from I to K has to be 8. Now let's find the length of IP. Well, here's IP right here. Well, from I to N, we have 4. From N to P, we have 1. So 1 plus 4 is going to be 5. So from I to P is going to be 5. So the answer is 5. Alright, MK. Now, we're going to use a right triangle here, okay? Here's my right triangle. This length here is 4. This length here is 8. This whole length right here is 8. That's your hypotenuse. This whole length here is 4. That's your leg. So using Pythagorean's theorem, 4 squared plus leg squared equals 8 squared would be 16 plus leg squared equals 64. That would be L squared equals 48. Take the square root of both sides. L equals square root of 48. Now, you're welcome to break that down, of course. 48 is 16 times 3. So cross the 16, put a 4 on the outside. So 4 square root of 3. Alright? 4 square root of 3. Number 17, MP. Well, here's M to P right here. Well, guys, once again, we got a right triangle, do we not? I'm going to highlight this right triangle in red, okay? There's a right triangle right there. Okay? So, let's see what we got here. The hypotenuse is 5. 4 plus 1, so this whole length right here is 5. That's your hypotenuse. This length here is 4. So we have Pythagorean's theorem. Once again, we're missing a leg. One leg is 4. The other leg, I don't know. The hypotenuse is 5. 4 times 4 is 16. 5 times 5 is 25. Bring the 16 over and make it negative. That leaves you with 9. Take the square root of both sides. L equals 3. Alright? So, we know the length of PM is 3. And then lastly, KP. Now, KP is this entire line right here. I'm going to erase everything. KP is this entire line right here. From K all the way down to P. Alright? Now, we just found MP right here. That's 3. And we just found MK right here. is 4 square root of 3. So to find the whole length, we add these two together. So we have 3 plus 4 square root of 3. Now students, you can't add those together, okay? Because one has a square root of 3 and one doesn't. Now if you want to type this whole thing into your calculator, get decimal, I have no problem with that. 3 plus 4 square root of 3 in decimal form would be 9.928, and that would be fine, okay? But I think the answer they have is 3 plus 4 square root of 3. Alright, so there we go. Moving on to this problem here. Now this problem was also on your quiz. And we've gone over this already when we went over your quiz, but we'll go over it again, okay? So here we go. Let's take a look here first of all at number 19. Okay, now arc CE, that means from C all the way to E. I'm sitting here trying to do this review sheet while watching NCAA basketball on my laptop to my left. That's probably not a very good idea, is it? Okay, I'll try to focus here. Alright, so arc CE is 121 degrees. They tell you that right here, okay? Now with that in mind, if this whole arc from here to here is 121, look, if this much is 59, then that simply means this one right here has to be what? 62. Because from here to here is 62, and from here to here is 59. 62 plus 59 is 121. Now something else, they tell us in the directions that we have circle Q. Now if we have circle Q, then this has to be a diameter, because this line is passing through the center. If a chord passes through the center, it has to be a diameter. If this is a diameter right here, then we have a semicircle from here to here. If we have a semicircle from here to here, that means we have 180 degrees. So if this is 180 degrees, then E to A must be 118, because 118 plus 62 gives you 180 for this semicircle. By the way, if this is a semicircle right here, half a circle, then what is this right here down here? Another semicircle, right? Well, we have 59 plus 36. That's going to be 95, I believe. So if that's 95, then this right here has to be 85. Because 85, if we add these up, I hope I did it right. 59 plus 85 plus 36 should give us 180. 59, 85, 36, 420, carry 2, 7, 15, 180, yes. And so there we go. Now with that in mind, we should be able to do these problems pretty quickly, okay? First of all, we're going to find the length of arc DE. Arc DE. So here we go. DE from D to E, 62 degrees. Now arc AE. So from A to E, the arc is 118 degrees. Now arc AEC. So from A all the way to E, all the way to C. Okay? So it's 118 plus 62 plus 59. Okay? From A to E to C. Alright? So we get 9 carrier 1, 3 carrier 1, 239 degrees. Now let's take a look at arc BE. Arc BE. Here's B going to E. Now some students on their quizzes went this way, I remember that. And that would be a major arc. If it's truly a major arc, then it's gotta have 3 letters. If you're gonna go from B to E this direction, then it's gonna be 3 letters, and we don't. We have 2 letters. That means the smaller minor arc. So from B to E is 36 plus 118. So 118, 36, 154 degrees. 154 degrees. Alright, let's take a look now at arc BDC. So it's 3 letters, okay? So we have to go from B to D to C. So it's from here all the way around the entire circle, except for this arc here. So just take 360 and subtract 85 degrees. Alright, 360 and subtract 85 degrees. 275. 275 degrees. And then lastly, arc BDA. So we start at B, we go to D, and then we go to A. So from B to D measure of CD. Alright, so here we go, CD. Now, what we've learned is this. We've learned that whenever a diameter, and this is a diameter, is perpendicular to a chord, and it's definitely perpendicular to a chord because of right angle right here, this diameter cuts the chord in half, and it cuts this arc in half also. Got it? So, if AD is 4, then DC or CD also has to be 4. Okay, that's from a theorem that we learned. Number 26. Now, we have, notice, a chord here and a chord here, and both of these chords are equidistant from the center of the circle. See, this line here is congruent to this line here, and they're perpendicular to, which you have to have, because remember, I hope you remember this, you cannot say that a point is a certain distance from a line unless it's a perpendicular line. So, this distance here is the same as this distance here. So in other words, this chord here is the same distance from the center as this chord here. So when that happens, the chords have to be congruent. So if AC is 20, then FD also has to be 20. So the answer would be 20. Number 27. Alright, now, once again, looks like we have the same thing. Here we have congruent chords. Okay, notice we have AB here is congruent to BC. Alright, so this chord here is congruent to this chord here. Now if that's the case, does it not make sense that the distance then has to be the same? We just talked about that. If two chords are the same distance from a circle, then they're going to be congruent. Well, if two chords are congruent, then they're going to be the same distance from the circle. Okay, so if PB is 15, then EP will also be 15. Moving on to number 28. Number 28, we're looking for BD. Well, guys, I'll be honest, this might be the easiest one we've done, although it looks really complex. But to me, it's pretty simple. B is the center. 2.3 is the radius, right? Sure it is. There's the center. There's the point on the circle. So the radius is 2.3. Well, if the radius is 2.3, then you take 2.3 times 2 and you get the diameter. The diameter would be 4.6. Why does that matter? Because the segment you're looking for, BD, is a diameter. It's a diameter. It's a chord that goes to the center of the circle. So BD has to have a length of 4.6. You didn't need all this other information at all. Okay? Alright, let's continue on to number 33. Alright, number 33. The directions for 33 through 36 says solve for x. So we're going to solve for x and we'll see how we do here, okay? The measure of arc AB from here to here, now watch carefully please students, is 136 degrees. Now if you've been learning your theorems and really understanding them, then you know that this line here and this line here form two angles. Here's one angle from this line here to this line here. And you know the second angle is this angle over here. Now those two angles are not necessarily congruent, but they are supplementary, by the way, because you have a straight line here. So those two angles have to add up to 180. But anyway, here's the theorem I want to talk to you about. We learned that when you have a, now listen carefully please students, when you have a tangent and a secant, or in other words a chord, we could also call it a chord here in this case, okay? Secant slash chord that intersect at a point of tangency, the arcs that are formed are going to be twice as big as the angle that formed the arc. For example, this arc here is going to be twice as big as this angle here. This arc right here, this arc right here is going to be twice as big as this angle formed right here from this line to this line. So we're trying to find the measure of arc. We're trying to find the measure of this angle right here from here to here. So let's take this one step at a time. They tell us this arc here So this angle right here is 68 degrees. Okay, so here's what you really have. You have a straight line like this. Like this. Then you have a line coming off of it like this. And this is what right here? 68 degrees. So what would this angle right here be? X. Well, guys, it's easy. Subtract from 180. These two angles here have to add up to 180. So 180 minus 68 would be 112 degrees. All right, number 34. Now, here, listen carefully. Here we have a secant and a tangent, not intersecting on the circle. Here we had a tangent and a chord, or a secant, intersecting on the circle. Here we have a secant and a tangent intersecting outside the circle. This angle that's formed right here is the difference of the two arcs that are intercepted. So the two arcs that are intercepted by this secant and this tangent, the two arcs would be this one here, there's one, and this one here. So you subtract those two arcs and then divide by 2 and you'll get this angle. So they tell us the measure of arc EG right here is 60 degrees. And they tell us that the mark of FG from here to here is 170. So subtract those two and divide by 2. 170 minus 60, 110, divide by 2, and you'll get 55 degrees. Alright, moving on to 35. Now here we have two chords intersecting inside the circle. Now when that happens, this angle here will put a dot, and this angle here, they're the same angle, right? Well, those angles right there are they're half of the sum of the two arcs that are formed. So this arc here and this arc here, you add them together and divide by 2, and you'll get this angle, which is the same angle as this angle over here. Alright, and that would also work for these other two parts. This arc here and this arc here, add them and divide by 2, and you'll get this angle right here. So let's see what they give us. They give us HK. So let's do that in blue right here. HK is 82 degrees. Alright, and IJ right here is 46. Alright, so if I add those two together, I get 128. Okay, add these two arcs together, then divide by 2, you get 64. That means this angle right here is 64 degrees. That means this angle right here is 64 degrees. So what about X? Well, guys, it's not too difficult to figure out. I mean, look, this is a straight line, is it not? And we have a straight line coming off of it. So we have a line like this and a line like this, and this is 64. Well, this angle right here and this angle right here, they have to be supplementary because we have a straight line, a straight angle with a line coming off of it. These two adjacent angles have to add up to 180. So the answer would be 116 degrees. 116 degrees. Alright, number 36. Here we have two tangent lines. Two lines that are tangent to the same circle, intersecting outside of the circle, okay? Two tangents intersecting outside the circle. Now what that means is this. This angle right here equals this, the two arcs that are intercepted, this arc here, and then the rest of the circle, this arc here. If you subtract those two arcs and then divide by 2, you will get this angle measurement right here. So with that in mind, let's see what they give us, okay? They give us LN is 86 degrees. So I'm going to highlight this arc right here in red. And put 86 degrees. Now we know that an entire circle from N all the way around the whole circle to here is 360. So if from here to here is 86, then I can take 360 and subtract 86, and I'll have the other arc left over. Alright? So the arc here in blue from L all the way to N, that blue arc is 274 degrees. So now that I know the length of these two arcs, what did I tell you to do? You subtract and divide by 2, and you'll get this arc right here. Or excuse me, this angle right here. So 274 minus 86 would be this right here, I believe, yes. And then divide that by 2, and you'll get the answer, which is 94 degrees. Alright? Okay, moving on to numbers 37 through 40. Here we go. They want us to write the equation of a circle, and boys, this is really, really simple because they give us the center and the radius. That's pretty simple, guys. So, I mean, if the center of the circle is 6, -5, change the sign of the 6. Quantity squared, always put a plus sign here. Change the sign of your 5. Quantity squared, and then your radius always gets put in, and then you square it. Now, I have no problem with this answer, none. However, the square root of 11 squares 11, so if you want to put 11, that's fine also. I have no preference. Number 38. Okay, the center is -4, -1, so x, change the sign of the -4. Square the parentheses, always put a plus sign, and then y, change the sign of the 1, +1, always square the parentheses, equals, always take your radius and square it. That is totally acceptable. Now, if you want to square 1/2, 1/2 times 1/2 is 1/4, and that's totally fine also. Alright, moving on to number 39. Alright, your center is 3/8, so change the sign of that, x minus 3/8. Quantity squared plus, change the sign of the 1, y minus 1, quantity squared equals, then we have the square root of 3 over 4, the whole thing squared. Always take your radius and square it, okay? So with that in mind, I have no problem with that answer there. If you want to square this, though, it's really not too hard to do. If you square a square root of 3, you just get 3, and if you square the denominator, which is 4, 4 times 4 is 16, so this is fine also, however you want to do it. Okay, moving on to number 40. Okay, let's change the sign of the 7, and that would be x minus 7, quantity squared. Always put a plus sign, always, when you're writing the equation of a circle. Change the sign of the 11, that's x minus 11, quantity squared, and that equals your radius squared, or 9 squared. This is a totally perfectly acceptable answer. If you want to put 18, that is also, or excuse me, 81, that is fine also, okay? Alright, moving on now to numbers 41 through 46, okay? The rows of beads lie on major or minor arcs. Well, guys, I mean, look, every single one of these arcs is bigger than a semicircle. Every single one of them. I'm not trying to stay on a certain line. I'm just showing you every arc is right on, every bead is right on an arc that's bigger than 180. So they're all major arcs, every single one. So major. The rows of beads lie between 6 blank circles. Now, what is the center of this circle, the inner circle? P. What's the center of the next circle? P. What's the center of the next circle? P. What's the center of the outside circle? P. All of these circles have the same center, so we call that concentric circles. So the answer to 42 is the rows of beads lie between 6 concentric circles. Concentric circles. Okay. Alright, moving on to number 43 is the measure of angle FPD. Let's see, here's FPD. So this angle right here. Is that angle equal to APC? APC, well, of course it is. I mean, A to P to C would still be you're still dealing with the same two rays right here. This ray and this ray here. So angle FPD is the exact same angle as APC. So yes, definitely, because it says explain your reasoning, because points D and C lie on the same ray, and points A and F lie on the same ray. So yes, they are going to be congruent angles. Moving on to number 44. Is this arc ABC from here to here, the same arc as DEF. I think they made a mistake there. I think this point here should be right here. But that's okay. Because I can't draw right. I think I did. I think I drew that correctly. But anyways, no, they are not. Now please let me show you why. If you will listen carefully, I will help you understand this. I mean, sure, just going from the naked eye and just looking at it, obviously the arcs, this arc here on the outside's bigger. But let's use some geometry reasons here, okay? Look, arc AC and arc DEF. Watch this carefully, guys. Do you not see how they have the same central angle? That's what can be confusing. They have the same central angle. Okay, look at that. So let's pretend for a second that the central angle here is, I don't know, 30 degrees. Then that means this arc here would be 30. And this arc here would be 30. But they're still not congruent. Why? We learned, guys, that the only way arcs are congruent is if they have the same measurement, lying on the same circle or on congruent circles. And this arc here is not lying on this circle here. They're not lying on the same circle, nor are they lying on congruent circles. So no, those two arcs are not congruent. Okay, moving on to number 45. Is angle ABC congruent, or arc ABC congruent to arc DEF? So arc A to B to C. Congruent to arc DEF. I see now what they're getting at, and I apologize for making a mistake. Okay, I misspoke at number 44, and I feel really badly about that, but okay, I see what they're saying now. I didn't read number 44 close enough. It says, is their measures the same? And the answer is yes. The arc, this arc going all the way around, is going to have the same measure as this arc here. How do I know that? Because they have the same central angle. Look, guys, let's just pretend this angle here is, I don't know, we'll say 50 degrees. I don't know. Well, if this is 50 degrees, then this arc here is 50, this arc here is 50. That means this arc going all the way around is 310, because I took 50 and subtracted it from 360. So arc DEF is 310. Arc ABC is 310. So yes, they do have the same measure. Sorry, I misread number 44. They have the same measure, okay? But 45, are the two arcs congruent? Are the two arcs congruent? No. They both have a measurement of whatever their measure is, but they are not congruent, okay? They are not on the same circle. They are not. Now, if the measure of AC is 60, so let's see, if this arc right here is 60, what is the measure of arc ABC from A to B to C? Well, the answer is going to be 300, because going around a whole circle is 360. If we have from here to here 60, then the rest of the circle is going to be 300. So the other arc would be 300 degrees. All right, moving on to numbers 47 and 48. You're visiting a museum that has a, I'm not quite sure how to pronounce this, a yurt, I guess, on display. You're not allowed to enter the yurt, but you'd like to know what the radius is. So because you are a math genius, you stand 5 feet from the yurt and measure 10 feet to a point of tangency. So here is a bird's eye view of the yurt. And there's a picture in your book, by the way, guys. You can look at this. Okay, it's right here. Okay, there's a picture of this in your book. looks like, okay? Alright, so here's a bird's eye view of what's going on here, okay? You're up in the ceiling looking down, and here's the kid standing right here, and he's 5 feet from the yurt. And then he measures a straight line to a point of tangency. Right there, we're stretching it a little. So that line right there, that measurement right there is 10 feet. Now, we did learn, let's continue this on to the center of the circle. Alright? And then come down like this. Now, now students, what you need to notice here is the distance from here to here is a radius, and the distance from here to here is a radius. So those two measurements will be equal. So if I call one of those x, I can call the other one x also. And how do I know they have a right angle here? Because of a good old theorem that we learned that said whenever a radius and a tangent line intersect at the point of tangency, they will form a right angle. They will be perpendicular. So I'm going to take that, I'm going to get rid of this mess and draw my right triangle like this so we can see it a little better, okay? So our hypotenuse goes from here to here. So from this point here to this point here is 5, and from here to here is x. So this whole length here is 5 plus x. This whole length over here is x, and this length here is 10. So, with that in mind, let's go ahead and use Pythagorean's theorem, solve for x, and we're finished, okay? Here we go. Well, one leg would be 10. The other leg would be x. The hypotenuse would be 5 plus x. You have to square the whole thing, okay? 5 plus x squared. Now 10 squared is easy. That's 100. And x squared is easy as x squared. This, on the other hand, is 5 plus x times 5 plus x. You must do it like this, okay, or you miss the problem. Now remember, take this 5, multiply it through. You should know that from Algebra 2 or Algebra 1. Then take your x and multiply it through. You should know that from Algebra 1. So 5 times 5 is 25. 5 times x is 5x. X times 5 is 5x. And x times x is x squared. So what you really have over here is x squared right here. And then 5x plus 5x would be 10x. Don't put 10x squared, just 10x. You're combining like terms. And then positive 25. Okay, we can solve this pretty quickly. Your x squareds cancel out. You have x squared here. If you brought over and made it negative, it'd cancel out. So your x squareds totally cancel out. Now bring your 25 over and make it negative, and you're left with 75 equals 10x. Now divide both sides by 10, and you're going to get 7.5 equals x. Okay, so there we go. We just found the radius, 7.5. Now if the radius is 7.5, then the diameter is going to be number 48. The diameter is going to be 15. Pretty simple. Alright, moving on to number 9 on the next page over, or a couple pages over, I guess it is. And let's go ahead and take a look at 9 through 12. Each circle's center is 0, L, the letter O. Find A, B. Boy, let's really pay attention now, okay, guys? Okay, first of all, we know this chord here. We know this chord here has a length of 12, okay? Notice also that we have a concentric circles, okay? This circle here has a center of O. This circle here also has a center of O. Now, if this is truly a circle right here, then this is a radius, and this is a radius of the small circle. So if that's the case, then I know for sure this segment right here with one mark has to be congruent to this segment here with one mark. They're both radii, guys. They're both a radius of the small circle. They have to be congruent. And now you say, well, sure, that's fine. But do we know for sure that this line here is perpendicular to this line here? Yes, we do. Because we have a theorem that says whenever a tangent line and a radius intersect, they're always perpendicular. distance from the center of the circle, then they're going to be congruent. So if this chord here has a measurement of 12, then AB will also have a measurement of 12. Number 10. Alright, now we're told here that this measurement right here, this arc right here is 140 degrees. Got it? And then we know this is 80. Alright? Now, real quick, we might need this. I'm not sure. We probably will. Let's find the measure of this arc right here. Okay? Now the measure of that arc is going to be 140 degrees. How do I know that? Well, starting from point A and going all the way around the entire circle is 360 degrees. So from here to here is 140 plus 80. How much more do we need to make 360? We need 140 more. Now, we have a theorem that says if two chords intercept congruent arcs within the same circle, then those two chords are congruent. So, I have this arc here is 140, and it's formed by this chord right here. This arc here is 140, and it's formed by this chord here. So when two chords within the same circle intercept the same arcs, then they're congruent. So if the AC is 8, then AB also has to be 8. Alright, moving on to number 11. Number 11. Alright, we're looking for the length of AB. Now, first of all, students, I would like to point out to you many things. Alright? First of all, I have a diameter right here. This is a diameter. Okay? That is a diameter of a circle. Now, I know that because this chord, passes through center O. O is the center of the circle. Okay, now I also notice that this diameter is perpendicular to DF, and it's perpendicular to AC. Okay, now when that happens, we know that this diameter cuts the chord in half and the arc in half. So if DE is 3, then EF is also going to be 3. So now I know this whole segment DF has to be 6. Now, let's move on. Now, notice this chord here that I'm highlighting in blue right now, or trying to highlight in blue. This chord right here in blue is equidistant from the center as the green chord is. How do I know that? Well, look, guys, these congruent marks right here. So, and also we know it's perpendicular, which is important when you're finding the distance from a point to a line. It's mandatory. So, this chord here, the blue chord, is the same distance from the center as the green chord is. So, that means the two chords have to be congruent. We learned that if two chords are equidistant from the center of a circle, then they're going to be congruent. So if DF is 6, then AC or AB is going to be, I'm sorry, I messed up. If the whole thing is 6, then AC is going to be 6. And if AC is going to be 6, then each of these little segments here have to be 3. How do I know that? Because I have a diameter that is perpendicular to a chord. And when a diameter is perpendicular to a chord, it cuts the chord in half. It cuts the chord in half, okay? So this right here, AB, is going to have a length of 3. Alright? A length of 3. Moving on to number 12. Number 12. Okay, we're trying to find the measurement of AB. I'm still trying to find AB. Here it is. Okay, we're trying to find the measure of this diameter right here. Okay? Well, let's see if we can do this. Oh my, this is pretty simple, guys. Really, it's very simple. O is the center, right? So CO is a radius, right? Well, if that's a radius, if your radius equals 8, then what does your diameter have to equal? 16. So, let me get my pen here. This here's the diameter. BA is a diameter. It's a chord that passes through the center. So it has to be 16 because it's a diameter. And I just showed you over here, the radius is 8, the diameter is 16, and this is a diameter. Okay, moving on to 13 through 16. We're going to find the measures of angles 1 and 2. Now these also probably look familiar on an old quiz, okay? Let's see if we can figure this out. I have a central angle right here. Everybody see it? Central angle, P is the center of the circle. So if I have a central angle is always equal to, I better pause. I never read the directions. What we're doing on the next 4 problems, students, is we are finding the measures of angles 1 and 2. The measure of angles 1 and 2. Okay, so this is a central angle, and a central angle is always equal to its intercepted arc. Or you can say an intercepted arc is always equal to its central angle. Okay, so I have a intercepted arc of 145 degrees. So the central angle also right here is going to be 145 degrees. So the measure of angle 2 equals 145 degrees. Now, what we have next is not a central angle, it's an inscribed angle. Remember, whenever an angle inside of a circle has its vertex on the circle like this, and the endpoints of its rays right here on the circle, that's called an inscribed circle. What arc is intercepted by those endpoints? Well, this arc right here. We learned that an inscribed angle is always half the measure of its intercepted arc. So if 145 degrees is the intercepted arc, angle 1 is half of that. So take 145 and divide it by 2. So the measure of angle 1 is going to be 72.5 degrees. Number 14. Okay, now, first of all, we have circle P, which means P is the center. So second of all, this has to be a diameter. Well, if that's a diameter, then this intercepted arc right here is a semicircle, is it not? Sure it is. Now, we learned, we had a theorem that said if an inscribed angle intercepts a semicircle, and it is. Here's your inscribed angle. I'm going to change colors in black. Here's your inscribed angle right here. The vertex is right here on the circle. And the end of this angle right here is on the circle. And the end of the angle right over here is on the circle. That black angle is an inscribed angle. Okay? So, we learned that if an inscribed angle intercepts a semicircle, then the angle right here is a right angle. So that's just a theorem that we learned. So the measure of angle 1 equals 90 degrees. Equals 90 degrees. Now, let's take a look at the measure of angle 2. Now this one here, really is just, again, like the last problem, or the last part of this problem, is just a theorem, guys. We learned a theorem that says whenever a line is tangent to a circle, like this little ray is here, and a radius intersects that line at a point of tangency, this angle right here is going to be a right angle. Anytime a tangent line and a radius intersect at the point of tangency, those two lines will always be perpendicular. So the measure of angle 2 is also 90 degrees. Okay, you need to know all of these theorems, guys. Alright, number 15. We also learned that if a quadrilateral is inscribed, its opposite angles are supplementary. Okay, that's the only way that a quadrilateral can be inscribed inside of a circle, is if its opposite angles are supplementary. Now, if you'll look at this shape that we have here, guys, it's an isosceles trapezoid. Okay, isosceles trapezoid. Now let me get this circle out of the way. I want to show you something. This is an isosceles trapezoid. We don't even need the circle to solve this, guys. We really don't. We do not even need the circle to solve this thing. If I tell you right now, forget the circle. If I tell you this side is congruent to this side, and this side is parallel to this side, you know right away you have an isosceles trapezoid. And if you have an isosceles trapezoid, then you know base angles are congruent. So you know, if you know your math, you know this angle is congruent to this angle, and this angle here is congruent to this angle here. Okay, we know that about isosceles trapezoids. Not only that, look, guys, if I have two parallel lines cut by a transversal, are not these consecutive interior angles here and here? They're not congruent. Well, they might be, but they're always supplementary. They're always supplementary. Okay, so with that in mind, do I not have parallel lines here and here? If I extend them, sure. Cut by a transversal, sure I do. So this angle here and this angle here, they're consecutive interior angles, so they're supplementary. So angle 2, well, first of all, angle 1 is easy. I just told you these top two angles are congruent. So if this angle right here is 105, then this angle over here has to be 105. So the measure of angle 1 equals 105 degrees. Okay, now we know these two angles here are supplementary, so this angle right here has to be 75, because 105 plus 75 is 180. So the measure of angle 2 is 75 degrees. Alright, moving on to number 16, and that should not be there. Alright, that's a different class, different assignment. Alright, now we're going to find the measure of angle 1 and the measure of angle 2. So here we go. Let's see what they give us. First of all, students, I think it'd be wise to kind of pull this picture away, just for a second, the circle away, or part of it away, okay? We have two secant lines intersecting outside of a circle, do we not? Sure we do. So I'm going to go like this, very carefully, and I'm going to pull this picture away. I'm telling you guys, it is so helpful to draw pictures. If you're taking a test or a quiz, draw the picture on a notebook paper without all of this, not gibberish, but just all of this distracting other lines you don't need, okay? That's all you need right there, is that right there. And that's good enough for angle 1, okay? So they tell us right here in black, this arc right here is 96 degrees. So from here to here, this arc is 96 degrees. This arc right here from here to here is 38 degrees. Got it? So we're going to find the measure of angle 1. Well, we learned a theorem that says when two secant lines intersect in the exterior of a circle, you can take the two intercepted arcs, subtract them, not add them, subtract them and divide by 2, and you'll get this angle here. So 96 degrees for this arc minus 38 degrees for this arc, and you're going to get 58 degrees. Now divide that in half and you get 29. So the measure of angle 1 is 29 degrees. Now let's go ahead and find the measure of angle 2 now, okay? I'm telling you, it helps so much to get a lot of the distractive other lines and stuff out of the way. Now for angle 2, here's what I need. Look guys, angle 2 right here is, I probably need this segment here and this segment here. See how those two chords are intersecting inside of a circle? I'm pretty sure that's all I need, students. Now if I'm wrong, then we'll add some more stuff later, but I'm pretty sure that's all that I need. So I'm going to pull this picture out of the way. Over to here, I guess. Now, of course my drawing's not perfect. Let's extend this a little bit and extend this. A lot of you guys are jealous. You don't have my drawing skills. I know that. Alright, this arc from here to here is 96 degrees. And this arc from here to here is 36 degrees. Now we learned something. We learned that when two chords intersect inside of a circle, you can find these angles right here. This angle here and this angle here, they're congruent. They're vertical angles. You can find their measure by adding, not subtracting, by adding the two intercepted arcs and dividing by 2. So this is angle 2. All I have to do is take this arc here 96, this arc here 36, and add them together, and I get 132 degrees. Now divide that in half, and you get 66 degrees. So the measure of angle 2 equals 66 degrees. Okay? Alright. Let's check it, make sure we're right like we always try to do. 29 and 66. Okay? Alright, students, I hope this review sheet help video has been a help to you. If you have any questions, never hesitate to call or email.